Hello, everyone. So this is the AP Physics C Mechanics Set 2 free response questions for the 2022 exam now. And what I've noticed actually just looking through these is that they are very similar to the Set 1 questions. However, I would still like to go over them just for the sake of completeness as well. So in this case, for question number 1, again, a very similar situation here. A small sled slides across a rough horizontal table with some initial velocity. There's some kinetic friction. And the device that is attached to the ground maintains constant tension in the string by unwinding the string as the sled slides to the right. And essentially, what we need to do is express a bunch of answers in terms of different constants for the problem, as well as the value of x, which can vary from 0 to L here. All right, so let's go ahead and move on then to the next page. So the first thing that we have to do is we do have to actually go ahead and draw the free body diagram for the sled before it comes to rest. So you can see that the sled is in contact with two things. It's in contact with the table as well as the string. So that means that we are going to have a total of 4 forces. We are going to have gravitational force. The sled does have some mass, so it has to have gravitational force. There is going to be tension at an angle. So we'll go ahead and write that down. Now, normal force, we do know has to cancel out both the vertical component of tension and all of gravitational force. So I'm going to try to draw it about equal magnitude. That's probably a little bit too small, but it's close enough. The main thing to note is that the vertical components of all of my forces must add up to 0. And then finally, we do have kinetic friction, which should just be pointed straight to the left then. So I'll label that F sub K. All right, there's our free body diagram. Now, in addition to that, what we do want to do is we do want to determine the angle that the string makes with the vertical when it has traveled a horizontal distance x. And if we head back over to the diagram, you can see that the angle is essentially in a right triangle with the values of y and x. So I can go ahead and write the tangent of theta is going to be x over y. Therefore, theta is going to be arctangent of x over y. Very similar again to set 1. You're going to notice that with a lot of these different questions. But now x is actually in the numerator of the arctangent as opposed to the denominator. Part C, we have to derive some expressions for forces. Normal force, just like last time, sum of all vertical components should add up to 0. That's going to be normal force minus tension sine of theta minus the gravitational force. And that, again, that should all add up to 0, which I've already written down. Let's go ahead and get rid of that. All right. And so that means that the normal force then is going to be tension sine theta plus mg being that gravitational force. And again, we do know that sine of theta, theta being arctangent of x over y. So sine of arctangent of x over y plus mg. There we go. Now, something I do want to actually note that I didn't do in set number 1 is I could simplify arctangent down. The reason why I'm not actually doing that is because, if you're going through and you're actually taking these questions on the exam, the chances of you actually thinking about how to simplify arctangent down are not very likely. You're going to be focused on trying to answer all of the questions and make sure that you have all parts answered to the best of your ability. And simplifying down arctangent, in my opinion, just kind of takes a little bit of time away from what you could be doing in order to solve some other questions. We can still analyze the arctangent fairly well, as we did in set 1 for the very last part when we were comparing the work done between 2 different segments. So, in case you are watching any other videos, or maybe in the distant future, you've taken a look at College Board solutions and you came to YouTube to get a better idea as to how to solve these problems, that's the reason I'm not simplifying down arctangent. just in case my answer is different from what College Board does provide when they do release their solutions. All right. Anyway, back to the problem now. So sum of all horizontal components is going to be equal to the net force, F net. Net horizontal force is what we're looking for here. Now, in this case, all of the horizontal forces are directed to the left. So it's going to be negative friction force minus Ft cosine of theta. Well, we do know that friction, as usual, is mu k Fn. And then we have Ft cos theta. So then we can plug in what Fn is from part C, part 1, and then theta from part B. So we get negative mu k, and then Fn is going to be Ft sine of arctan x over y plus mg. And then again, we still have to have Ft cos theta, so Ft cos arctan of x over y. And that would be our final answer then for this part. Again, it's a pretty long expression. There are a couple of ways to simplify it down, but for the same reason, I'm not going to do that. All right, and so part D then is asking us to derive an expression for the work done by the string on the sled as it moves from 0 to L. So we do know that work done is equal to force dotted with displacement. Again, force is negative. It's pointed in the opposite direction of the displacement. So I'm actually going to get a negative sign outside. So the bounds are from 0 to L. That's what x actually ranges from. So negative integral from 0 to L of the tension force. And keep in mind, we have to have the cosine of theta and then dx. Well, as usual, we can plug in whatever we had for theta. So Ft cos arctan of x over y dx. And there we go. There's our answer. All right, the sled comes to rest after traveling a horizontal distance to L, and we want to figure out, is the energy dissipated by friction greater in the first half or the second half of the motion? And much like in set 1 again, we do actually need to analyze the arctangent function. If you have simplified arctangent down using geometry, you can analyze that function as well. Again, you get the same results either way. So let's just go ahead and analyze arctan of x over y. So here would be x over y, and then we would have x over y down here as well. So the thing to note is that when x is equal to 0, we get cosine of 0 in our work done expression, which is maximized. And then in addition to that, you see that as x gets larger, then the area actually ends up starting to, then the actual function ends up actually starting to taper off. So we have arctangent right here. And then if I say that x goes to be very large, right, maybe 2L, for example, then what I'm going to notice is that as x gets much larger, arctangent is actually going to get closer to pi over 2. So that means that as x gets larger, or x goes to 2L, cosine decreases. And if cosine decreases, we're actually going to see a reduction in the amount of energy dissipated, because then the integrand gets much smaller. And so in that case, we are going to have that E1 is greater than E2. For the first half of the motion, the energy dissipated is larger. And again, the reason why is because the integrand is larger for the first half of the motion. And how do we know that? Well, we know that because near x is equal to 0, cosine is going to be a maximum. So cosine is at a maximum according to our expression. All right, and that is it for question number 1 then. So for question number 2, what we want to do is we want to do a similar situation again as usual to set number 1. And you see here essentially that part A is saying that the impulse from block 1 from the spring is given by JS. And then it's asking the impulse for on block 1 from block 2 during the collision is J2. and we need to figure out how those compare. So this one's actually quite a little bit different, not too much different, but a little bit um, from what we saw in set number one. Set number one was just asking us the impulse from one block on the next one. Here, we're asked about the impulse on block one by both of the different objects. And in this case, the answer is actually going to be that the spring impulse is larger than J2, simply because M1 starts off at rest, and then it moves faster before the collision so it moves faster between when the spring hits it and the collision than after the collision. Now keep in mind that M1, however, does not come to rest after the collision. Therefore, we have a larger magnitude of change in momentum due to the spring, because the change in velocity is greater. Mass one itself does not change its mass, so we end up seeing a larger change in momentum if you go from rest to some velocity, but then your velocity ends up decreasing just a little bit, but not all the way back down to zero. All right, so let's go ahead and move on to part B then for question number 2. So something that's important to note is that M2 is actually smaller than M1. So I'm going to go ahead and actually make a note up here about that. And what we need to go ahead and do then is we do need to go ahead and actually draw graphs for the magnitude of momentum for both blocks as a function of time. So I'm going to go ahead and say that what we're going to have is, after the collision, it's pretty obvious, I think, that you're going to end up having some constant momentum for block 1 and for block 2. Now, block 1, again, being more massive than block 2, it's only going to lose a little bit of momentum as opposed to losing a lot. All right, obviously block 2 starts with no momentum because it's not influenced by the spring. So block 2's graph will just look like a step function, essentially. Now, regarding block 1, something I do want to say is that block 1, if we go back to the problem here, and please ignore the drawings right now, otherwise I'm going to have to redraw them later. So the thing to notice right here is that the spring starts off as being compressed. And so something that's important to notice is that this is actually an oscillatory function. When the spring goes back to equilibrium, it is not any longer, when the spring goes back to equilibrium, it is not going to exert a constant force, and therefore the block is not going to have a constant acceleration. So the plot should not be just a straight line for the first half of block 1's momentum. Instead, what I would expect would essentially be something like a sine function, the first quarter of a sine function, in fact, where it starts off at 0 for the velocity starting off at 0, and then it ends up increasing to a maximum then. And so essentially what's going to end up happening, and I actually did draw that incorrectly, because it's not going to just gradually and then all of a sudden stop at the same momentum. It's actually going to go up, and then right when that collision happens, it'll drop, indicating that there is an impulse being exerted on block 1 by block 2. So that's better. All right, part C, show that the velocity is given by this equation after the collision. So we can use conservation of total momentum and conservation of energy. Momentum during the collision, energy when the spring is providing kinetic energy to the block. So we have 1/2 k delta x squared is equal to 1/2 m1, because m1 is what's being influenced by the spring, times v1 squared. v1 is the velocity before the collision, like right before the collision happens. And then conservation of momentum, m1 v1 is equal to m1 v2, m1 plus m2 times v, v just being the final velocity after the collision. So I can go ahead and solve one of these for velocity. I am going to solve the energy equation for velocity. And so what I end up getting is I get that V1 is equal to root K over M1 times delta X. And so if I go ahead and I plug that in into my momentum equation and I solve for V, then I'm going to find that I get the answer as requested, root K M1 over the sum of both masses times delta X. So there we go. All right. Now, if I go ahead and take a look at part D, I am given some stuff. I'm given that the mass of block 1 is 0.5 kg, and I am also given that the spring constant is 150 newtons per meter. So I have to go ahead and graph. This is going to be a little bit tougher because I'm actually drawing on my tablet, and I don't exactly have a ruler there. So let me actually go ahead and just draw an auto line like that. All right, so that looks approximately good for our best fit line. It's not as good. I have a lot more fun actually creating those graphs by hand, but it is what it is. All right, so there's my best fit line. Now I have to actually use the best fit line to calculate the mass of block 2. Now note that the rise over run is slope, so V over delta X is slope. And according to our equation, that's going to equal root K M1 over M1 plus M2. And so therefore, what I can do is I can solve this for M2. M2 is going to be root K M1 over slope minus M1. And so therefore, M2 is equal to root 150 times 0.5 gives me 75. So root 75 over the slope minus 0.5. Now I do actually have to figure out that slope. And so in terms of what that is actually going to be, I need to take 2 points on my best fit line. It looks like approximately, and let me actually go ahead and change my color so you can distinguish. It looks like approximately that point and this point. Those 2 red dots will actually be the best ones to use. They might not be exactly on the line, but they're close enough that I don't really mind. So the first point is 0.065, 0.7, and the second point is 0.055, 0.6. So I end up getting a slope of 0.1 over 0.01, which is going to be a slope of 10 then. So root 75 over 10 minus 0.5 is going to give me my mass. And in terms of what that actually is, I'm just going to go ahead and crunch it on my calculator right here. So I get 8.66 for root 75 divided by 10. And then I subtract 0.5. And that will give me an answer of 0.37 kg. Let's go ahead and move on to the next 2 pages then. So we are going to finish off question number 2, and then we'll go ahead and move on to question number 3. So after the experiment, the student uses a balance. We find that M2 is greater experimentally than what we would have expected. So M2 is greater in the experiments. Now, the student, one of the students, decides to remeasure the spring constant, and we get a higher value of K prime. And so we're asked, a different value K prime. We're asked if it should be higher, less than, or equal to. And the correct answer is actually higher than, because M2 is greater in the experiment. So if K was incorrect, then we would expect that because M2 is proportional to root K, K prime is greater to yield greater accuracy. So much like in set 1 again. Set 1, it was less than because block 2 was lower than determined before. All right, and so that does it then for question number 2. Now, finally, for question number 3, we are given a very, very interesting situation here. where we have a board with a pivot. There's a stretched and unstretched spring on one side, and a student is holding the second side of the board and then slowly lowers and releases the board. All right, and so essentially what we want to do, the first thing we need to do is we do need to actually draw and label the forces while the board spring system is in equilibrium. So what we are going to have is we are going to have a spring force. That spring force, of course, is going to act where the spring is located. So I'll put F sub S for the spring. And then in addition to that, we are going to actually have gravitational force for the board. Now, gravitational force does not act at the pivot, it acts at the center of mass. This is a uniform board. So let's go ahead and draw the gravitational force. Now, in equilibrium, the only other thing in contact is actually the pivot, which is at L/4. So here is the pivot force then, which I'll call F sub. I'll go ahead and actually call it F sub pivot. I called it F axle in set 1, but here they do specify that's a pivot, so I just want to be consistent with their terminology. All right, and do note that the pivot force should cancel out both the spring force and the gravitational force. All right, so after that, what we want to do is we are asked to derive an expression for the distance that the spring stretches when the board is in equilibrium, and then go ahead and write our answer in terms of K, L, M, and physical constants. Now, because we're in equilibrium, it actually does make more sense to use sum of all torques is equal to 0. In set 1, I used conservation of energy, and I think I did so incorrectly because if you use the sum of all torques is equal to 0, you get my answer just without that extra 2 in there, which I believe is actually the correct answer. So in terms of this question, let's just go ahead and say sum of all torques is equal to 0. So if I assume that the pivot is, well, at the pivot point or the axis of rotation, then that means that the torque caused by the spring minus the torque caused by gravity is going to equal 0. And so the spring force is going to be K delta X in terms of magnitude, and it's going to act a distance of L/4, right? Torque is equal to RF sine phi. And so the torque from the spring force is actually acting at a quarter of the rod's length away. Likewise for the gravitational torque, right? Gravitational force is going to equal mass times G, and then RS is also going to equal L/4. The reason why it's negative is because gravity would cause a clockwise torque on the board. So we get K delta X L/4 minus LG L/4 is equal to 0, or in other words, delta X is equal to mg over K. All right. And so the next part of the question is saying that we have a student pushing the board, therefore the spring is going to be stretched. And then essentially what happens is we release the board, and then at time t equals t1, it ends up first crossing the horizontal. And we need to actually this time do magnitude of the angular acceleration as a function of time between t is equal to 0, and t is equal to t1. So in terms of what that is going to look like, we are actually going to start with angular acceleration, because as soon as we release the board, there is going to be a net torque. Now that net torque is given by that spring force minus the gravitational force overall. And the important thing to keep in mind is that this is not a constant torque, because the spring force is going to decrease as time goes on. So what I would expect to see would be that when the board crosses the horizontal, that would be the equilibrium, because once I've removed my hand, we end up with the situation back in part A. So I'm actually going to see something like a cosine function then. And that is actually an incorrect cosine function. I do apologize. Yeah, that was actually a cosine squared. What this cosine should look like is something more along the lines of, I do apologize, I'm not very good at drawing cosine functions, especially on a tablet. something closer to that, because then if I were to go ahead and extend this, I would see that I would end up with something like that then. Okay, so let's go ahead and erase the dotted lines. They should not be a part of our solution. So this is what the graph should look like. It's an oscillatory function. All right, moving on to the next part then. We got, let's see, how many more parts? Okay, 2 more parts left. All right, so what we want to do then is for the next part, we want to derive an expression for the angular acceleration immediately after the board is released. Express our answer in terms of all of those things that you can see. So right after the board is released, it looks something like this. And so we have gravitational torque, and then we also have torque from the spring. And here is our pivot point at L/4 again. All right, so I'm actually going to go back 1 slide just to ensure that I can mark that angle correctly. So I'm actually just going to go ahead and mark it right here. So here's our dotted line. Here's the angle, theta naught. All right. And so that's going to be the angle between these 2 lines right here. All right. Okay, perfect. And so let's go ahead and move back then. Here we go. And essentially what I need to do is I need to say that net torque is equal to moment of inertia times angular acceleration, which I'll call alpha naught to be consistent. All right, net torque is going to be the spring, the torque caused by spring minus the torque caused by gravity, and that's going to equal angular acceleration times alpha naught. Now the torque caused by the spring force is going to be equal to k delta x times L/4, right? Force times distance from the pivot points, but now we actually need to have an angle. We're going to require quite a bit of geometry right here. If I go ahead and I draw another line, I actually notice that this angle right here is 90 minus theta naught. So therefore this angle and this angle are both also 90 minus theta naught. So it's actually going to be sine 90 minus theta naught, which actually happens to be cosine of theta naught. And if you just leave it as sine of 90 minus theta naught, that is perfectly fine. It's still a valid solution. So minus mg L/4 cosine of theta naught. I'm just going to go ahead and do that right now. Okay, and that's all equal to I times alpha. And so therefore, what I'm going to end up getting is I will get alpha naught, excuse me, I keep forgetting the knots here, k delta x L, let's go ahead and actually take the L out, k delta x minus mg cosine of theta naught all over 4 times the inertia. All right. And then finally for part D, we're now adding 2 masses onto the 2 sides of the board as shown. So the board is now pushed down and we need to figure out whether the angular acceleration will, how the angular acceleration will change, if at all, compared to in part C. And now there's a couple of interesting little things here, because what ends up happening is the board itself actually has the same inertia, but what's actually changing is now you have torques acting on it. Now it does actually say that the 2 masses are equal distant from the pivot point, and so therefore you are actually going to end up having the same angular acceleration because the net torque doesn't change. So something that I realized is that angular acceleration is actually going to go down. Net torque for the system is still constant. However, the inertia actually goes up due to the 2 masses on the board. So angular acceleration goes down. Sorry for that error in my work. And that does it for the Set 2 Mechanics 2022 free response questions. And so thank you for watching. I hope that you learned something from all of this as well. And I hope to see you all in the next video where we talk about the E&M questions. Thanks again.